So today we will actually, in some sense, it'll be the last lecture on regression, but I will actually uh, talk a little bit about a seemingly different problem of collaborative filtering, recommendation, or missing value estimation. And we'll see how regression naturally comes in. And then we will actually give you a homework today on the Netflix problem. So Netflix, I think about nearly probably been about 20 years ago, they came up with a competition where they gave training data, they released training data, or subset of ratings that they had. Uh, I think it was about 20,000 movies, maybe 500,000 users or anonymized users, and they said that on a held out data set, they were achieving about 0.95 root mean square error. And they posed a challenge and said that if anybody can improve the performance by 10%, so about 0.85 root mean square error, then they would actually give that team $1 million. So it was the Netflix $1 million challenge problem. And it actually spurred on a lot of interesting work in machine learning, in particular in recommender systems. And we'll see one aspect of it where uh, regression naturally comes and plays a role. So I'll talk a little bit about that, talk about the problem, and then we will assign that as a homework. And this homework will be available to you on Canvas, and it'll be due next week on Friday. So before I start, any questions? Okay. So let me kind of review a little bit about what we spoke about last time. We talked about regression, and in particular regularization in regression. We took in a particular example about univariate polynomial fitting, and uh, I showed you some slides from the Bishop book, which we will also upload, where if you uh, use too uh, high a degree of a polynomial to fit, you end up fitting the training data exactly, but you actually end up doing a poor job on the if a new test point came up, right? So that's the phenomenon of overfitting. And then we saw that one of the ways in which it was manifest is that many coefficients were very large. And so we tried to, we basically ended up adding penalty on the size of the coefficient terms. And when you add the penalty as sum of squares, which is the norm of W square, then we get ridge regression. And we looked at ridge regression and we saw it actually, solution is actually very similar to a classical least squares problem, except that you have lambda I over here. But then we also analyzed it using the SVD, so not just a computational tool. And we compared it to the least squares regression problem, which is essentially an orthogonal projection onto a particular range space. And we saw over here that this was in some sense, like uh, uh, a case where the small singular values kind of are regarded as noise, and they would be set to 0 in a smooth way using ridge regression, and the large singular values would essentially be preserved and would be equal to 1. So that kind of helps you a little bit better in understanding what ridge regression does. And so you can think of it as a little bit of this phenomenon called shrinkage, which is you take the large singular values, you kind of keep them, and the small singular values, you kind of shrink them towards 0. Okay, we gave a geometric interpretation also of ridge regularization that, if you were doing just least squares regression, you would just be, these points over here, which are the global minima, right? And so that would just be the solution. And these are the level sets of the quadratic functional that's in the least squares problem. Um, And you can think of ridge regression as saying that I'm going to make sure that my coefficients are have L2 norm square less than equal to a certain value, and that's given by this sphere. And so when you minimize f of w subject to the constraint that your variables lie in this region, then you get this solution, okay? And then we didn't do too much. We just introduced the lasso, which is instead of the squared penalty, we have absolute values, and so that can be thought of as, all my coefficients where the L1 norm is less than a particular value is captured by this surface. And you can see that this surface has corners. And as a result, when you minimize f of w subject to your coefficients living in this space, you kind of end up getting sparser solutions. Note that this, obviously I'm drawing in 2D, but your computation is actually taking place, or your model is lives in a d-dimensional space. Okay, so we will kind of use a little bit of that material, and today we will look at the problem of a special problem in missing value estimation. Okay. And in particular, this problem comes up in the problem that we are going to talk about, comes up in recommender systems. Okay. And again, the particular problem that we are going to talk about is also known as matrix completion. And we'll see why it is called that, or matrix factorization for recommender systems. Okay. So I told you a little bit about the next Netflix challenge. Okay. So suppose you have a bunch of users. Okay. So let's assume that there are M users, and, obviously M could be in the hundreds of millions, even billions now, right? And you have movies, or they actually could be, some items. For example, let's say on Amazon.com. Okay, and you have M users, and suppose you have N movies, right? And typically, users will rate a subset of their movies, right? So suppose there's a particular user, and he might say that they did not like this movie at all, so they gave it a rating of 1, but then they liked this movie a lot, which is they rated as 5. Okay, maybe I won't draw the circles. Okay, so 1, 5. But, a user typically doesn't rate, all the movies, right? They can't even watch all the movies, clearly, right? And they may not also rate all the movies that they watched. Okay, you can maybe get an implicit feel for that, but there'll be many movies where we don't know their rating. Okay, so maybe another user really liked this movie that this other user hated. They also like this movie, and maybe this user is a little bit like the first user, where they did not like this movie and like this movie, and so on. Okay, so there are many ratings, okay, over here. And the question is, suppose there is a particular user movie pair, what is its rating? So yes, it's easy if this user has already rated this particular movie, but otherwise you have to try to infer if these missing values. And the goal of, a recommender system might be to increase engagement on their platform. They want to recommend movies that, you might actually like. So they want to recommend movies where the prediction, let's say, is above 4 or 4.5. Okay, so we have ratings matrix. Sorry, ratings matrix. And let me denote that by R. Okay, and so I have this matrix now, which is R. Notice that it's actually going to be very sparse. Okay, if you think about all possible user movie pairs, it's M times N. But a pretty typical user might only rate, tens of movies or hundreds of movies, or maybe even thousands if they really like rating, right? But the number of movies might be, in the millions. So this matrix is going to be actually extremely sparse, okay, with many. And when I say sparse, that means there are many, many missing values. Okay, 99% or more of this matrix may be missing values. So the goal over here, okay, the goal, okay, and now you can start seeing parallels with the regression problem that we've talked about so far, okay, is that we are given ratings, okay, we want to predict the missing values. And these would be the actual recommendations. So that's the problem that we will be looking at, okay, predict any kind of arbitrary missing value. In real life situation, what you really want is you want to predict the top K, right? Maybe the top 10 or top 20 movies that that a particular user might like that they have not seen. Okay, so that problem is similar, but actually slightly different because you don't care whether a user is going to rate a movie 1.5 versus 1.7, right? Because they don't like those movies, so you would never really surface them. Okay. But now let's look at it. So any thoughts about how this is like a classical recommendation problem. Any thoughts on how you might end up solving this problem? Like how do you guys, try to figure out what movies to watch on Netflix? I guess Netflix already gives a recommendation, right? So, but how would you think about solving this problem? Suppose you are only given this particular matrix. Oh, there's something on the chat. Let me show, sorry. Okay, so Rishabh said, find users who are similar to others and then fill in the ratings based on the other users' average ratings. So great, right? Actually, some of the initial first work on collaborative filtering was based on this KNN kind of approach. KNN being K nearest neighbors, right? So you find out neighbors, right, who are similar to you, and then you use their ratings to infer these ratings. So that is, a fine method. And today we will look at, if we later on look at it, we'll see that it has certain similarities, but it's actually a little bit more of a global method. Okay. So let me just put what Rishabh kind of suggested, right? So initial methods, and these were actually some of the methods that were used in the, I want to say late 1990s, right? When Amazon, for example, was coming up. And if you look, there are certain papers on recommendation systems over, how to recommend items to users who, may have already bought some things. Okay. So the idea is you look at neighbors of a user. And when I say neighbors, I mean people who have similar ratings.
I guess even
Of item.
today, when you buy something from Amazon, it shows you a list of people that buy this also buy those.
Right. And
That
actually, those have the kinds of methods that I'm talking about are actually used over there. Was there a question, Hormuz, or you were just making a comment?
I'm just going with that, method that
Yeah.
you mentioned, and you mentioned that Amazon was using it and said, and
Oh, yeah.
still see that they're using something similar.
Oh, yeah, yeah. And it's actually a big driver of their products, right? Because it basically comes up to how people discover maybe things which are new to them, they might not have seen before, or things which, have high ratings or people have liked. Okay. So yes, definitely. I did not mean to say that, they were using them and they don't use them, but I just mean to say that they were actually, one of the first companies that needed those recommendations, right? At a large scale. Okay. So what we will study is, I talked about matrix completion or matrix factorization. And this is the problem, by the way, you are getting in your homework, right? So we are giving you a data set and you will basically implement this procedure. And you'll see that there are some subtleties that will come up when you try to implement it. Okay. So here is the matrix R. Okay. Suppose it has, ith row, and this is the jth column. Remember, this matrix is users by movies. There are M of users and N movies. Okay, this is the matrix R. And suppose, if I look at the jth movie, suppose it has been rated by a few users. And suppose I look at the ith user and they've rated some movies. And what I would like to find out is, what is this value? Okay, and that is Rij. Okay, and Rij the ith user might not have rated the jth movie. So the model that we used, the model actually that was quite successful in this competition, right? The winning team actually used that as one of the components, was the following, right? That I'm going to represent it. So the idea is kind of similar to the singular value decomposition, but there'll be differences that I'll talk about. That I'm going to say that I'm going to factor this as U M transpose. Okay, and this matrix U is M by K. K by N. Okay, and the model is the following, right? And K is typically going to be much smaller than Mn. So much smaller than min of Mn. Okay, and the model is that if I just said that there is a approximate sign over here, so approximate equality. So what you're doing is you're saying that if I look at this overall ratings matrix, I can actually factor it, and that there are latent factors. There are K latent factors that I can factor it as a product of the user matrix and a movie matrix. And in particular, a rating Rij is actually going to be given by the product of the ith row of U, so let's call it Ui transpose, and the jth column, which is Mj transpose. So my model is the following, that Rij is, again, it's a simple model, right? I'm not saying that this is exactly what different places use currently, but but it was actually quite successful. So I don't want to say that it is very, very simplistic. Okay, so it is UI transpose times MJ. Okay, and you should convince yourself that U of M transpose is a rank K matrix. Okay, so that's the model. That's that R is approximately equal to UM transpose. Okay, and let me just kind of, I've already written it, but this was ith row, jth column of M. Okay, so row I of U is UI transpose. Okay, so you can think of it as it is a low dimensional representation of the ith user. So low dimensional, and what is it? K. K dimensional representation of user I. Okay. Similarly, if I look at this is M transpose, so I can say that row J of matrix M is MJ transpose. Okay, and this is the low dimensional.
Excuse me, is it the jade
movie
row or
J.
the jade column?
What's that?
Is it the jade row of the J column of the M?
No. So remember that so just keep in mind the notation I'm using. This is M transpose.
Got it.
And over here, I said row J of M.
Yeah.
Is that clear, Hermes?
Yes, thank you.
Yeah. So I'm just, yeah, but it is exactly this, this particular column of M transpose, right? So row J of M is the same as column J of M transpose. Okay. And in particular, like I said, if I look at columns, columns of U, columns of M. So if I look at columns of U, right, these you can think of as the different latent factors. Right? And that is you can think of these as some features, some extracted features, okay, for users. Okay, and these are latent factors, features for movies. And if I actually remember, there are this, it's not just for Netflix, but I believe it was also used for dating websites. Like I think eHarmony even used to advertise that they had like a 30-dimensional representation that they could build. They did not say that in exactly these terms in their commercial, but they would say that, they basically extract out 30 factors for making sure that the people they matched up with were compatible with each other. Okay, so another example where you have, in some sense, matchmaking, trying to match users and movies or pairs of people together. Okay, so now the question, of course, is that this is the model. How do you actually find the UIs and the MJs? Okay, remember that I have that Rij, I want to be approximately equal to UI transpose MJ. So any thoughts on how I would find U's and M's? So I'm given the R's. But remember, this matrix is sparse. These matrices are actually going to be dense, right? And given this, that's all the information I have. There may be lots and lots of users, there are lots and lots of movies. From that, I want to get this.
It sounds like a partial SVD.
Right. So, this is a low rank matrix. We talked about the K truncated SVD. So it sounds actually related to an SVD, right? And one of the things that the SVD does is it uses, the squared loss, right? Or the square, least squares, the loss that comes up in least squares regression, right? So we could, and that's a natural thing to do, is that we look at a loss function, which is the quadratic loss, squared loss. So when I say that Rij is nearly Ui transpose Mj, then I can say that, let me look at this, and somehow, I can sum over all Ij, and then I can try to minimize this over all the u's. Now, how many u's are there? U1, U2, through UM. There are M users. And then I have movies, M1, M2, M. Oh, so is this solution, is it just given by, because I can write this as in matrix notation, no need for the sum, right? We learned about norms, right? So I can write this as R minus U M transpose Frobenius norm square. Is that correct?
Yes.
Also, can I just use the SVD then to solve it? Because remember, I want to minimize over U and M.
Yeah, but what do we put for the missing values? Do we just put 0 in there?
Aha, right? So that's the critical difference or importance. Okay. That this objective, thank you, Hormuz. Yeah, that's exactly the point. That this Ij is not over all M and N. If I knew all Rij from I equal to 1 to M or J equal to 1 to M, which is that all users have rated all the movies and so on, right? Which is, of course, unrealistic, then this problem would be solved by the SVD. But that's not the given problem. The problem is that you only know certain indices. So let me say that K is the set of all known ratings. Okay, so K is all the pairs Ij such that Rij is known. And so I'm trying to fit the training data, the model to the training data. So this is over all pairs that are known. So this is what is the important difference, right? Which makes this problem very different than the traditional singular value decomposition problem. So this is our objective. Okay. And I can write this in matrix form as follows. That I can write this as W element wise dot, where this is this matrix Wij, this matrix W has entries Wij, which is 1 if Ij belongs to K, and remember K is the known ratings. or is 0. And dot is the element-wise product. Okay, and that also has the name called Hadamard product. Okay. So is it clear so far what I've talked about? Any questions? So this is our model, UM transpose, and I'm trying to fit it to the training data. And the training data is exactly this. IJ belong to K. And then, we've talked a little bit about regularization, right? So typically, we do want to see regularization, and you'll see as you do the homework that regularization is very important also, right? So the regularization we'll do is ridge regularization, and that is plus lambda summation of ui square. I is 1 through m plus, plus lambda summation I equals 1 through n mj squared. Okay, and I can write that as lambda u Frobenius norm square plus lambda m squared. Okay, so this is adding.
Sorry, do we use same lambda for U and M?
You could try different lambdas too. So that you could do experiments with. I forget in the homework whether we have same lambdas or different lambdas. In the homework, we've given you the same lambdas. I think when people tried it, it did not make too much difference whether they use the same lambdas or not. Okay, you could actually also end up using, different sets of lambdas, right? Users who had rated more movies versus users who had rated less movies. But right now, we'll just assume that the lambda is the same. Does that answer your question?
Yes, thank you.
Yeah. Okay. Okay, so now remember that if my problem, right, if K is the set of all ij, okay, then the problem would be of the following form. Summation of I equals 1 through m, summation of j equals 1 through n, Rij minus ui transpose mj square. Okay. And again, minimize over u's and m. And that would be equivalent to minimize um r minus um transpose. Okay. And the solution would be given by the K truncated SVD. Okay. But as I have said that, and let me just write it to reinforce it, right? But in our case, we only know ratings that belong to a subset of all possible pairs, right? So ij that belongs to a given K. So again, to emphasize, we do not no or Rij for all ij. Okay. I is 1 to m and j is 1 to m. Okay, so we cannot use the procedure to compute the SVD. Now that's another also thing that we haven't really studied is how do you actually, given a matrix, how do you actually compute its SVD? It's actually not trivial, right? But we know that you open up Python or you open up NumPy, right? You will find a procedure to find the SVD. But we cannot use that procedure. So any thoughts on how we might go about solving this problem? We need to solve this problem over here. I've kind of given you a little bit of a hint. I've talked a little bit about regularization. I've mentioned regression to you. So does this look like a regression problem?
It is, and it should be solvable with some gradient-based method thing.
Yeah, yeah. Remember, what are the variables that we are solving for? It's u and m. Okay, so there's something that we can do. We can use a procedure called alternating minimization. Okay. And what this procedure does is the following, right? So it first does fix, so it starts with some u. Maybe I should just say that. Okay. Start with some u as a guess. Okay. Now, given this u, right, fix u and compute m. Okay. Now think a little bit about this, right? Suppose I'm given a u and I'm trying to do this problem, right? And what you can do is you can look at only one column of R, right? Then you'll have that the ith column or the, let's say the jth column of R is equal to, you know, your fixed U and the jth column of M transpose and square. Okay, and of course there's a regularization also. But my question is, can you solve that problem? Fix U.
Yeah, that's a normal regression problem, right?
So that's least squares regression. That's exactly what we've studied so far, right? So let me come to that, but the algorithm is actually going to be this, right? Start with some U, fix U and compute M, right? And then fix M and compute U, okay? And repeat, let's suppose capital K times, okay? So you would start with some U naught. You would get M1 from it. Then you fix M1, you get U1 from it. You fix U1, you get M2 from it. You get U2 and so on. Okay. And remember what MI would be. Mi would be obtained by a procedure where I'm minimizing over M R minus U, let's see, I minus 1
Yes.
times M transpose Frobenius norm square, okay, plus lambda. I have this regularization also. Okay, so I'll be solving this problem. And Mi would be the minimizer or argument of this problem. Okay. And similarly, Ui would be the argmin over U R minus U M I transpose Frobenius norm square plus lambda U square. Okay, so let's look in detail at what happens. Okay. Let's fix well, if I have R is nearly equal to U M transpose. Let me flip this around. R transpose is nearly equal to MU transpose because let's see. So I think I'll just fix M first and then compute U. Okay. I guess I can do either one of them. Okay. But right now, suppose we fix M. The other case would be very analogous. You would just be working with the transposers. Okay. So let me just draw this out. So this would be the matrix R transpose. Okay. So R transpose is number of movies by the number of users. And I want this to be equal to M which is N by K. So this is the matrix M and U transpose. Okay, and this is M. Okay. And let's look at this is ith user factor UI. Okay, and what I'm saying is that I want to look at the ith column over here. Ith column. Let me call that as Ri. So I have Ri is nearly equal to M times UI. Is that clear? Okay, Ri is the ith column of R transpose. Okay, so what I can try to do is Ri minus M times UI square okay, plus if I add regularization. So remember now, this is like our coefficients W. This is like my matrix X. And this is like Y. Okay, Y is replaced by Ri. X is replaced by M. And this is like our coefficient W. Okay, so I have this. And I want to try to find out the minimum over UI. So is this the problem we want to solve? So this looks exactly like a ridge regression problem. And then I can basically solve it for any I, right? What is the mistake that I made? So remember, Ri is the entire ith column. Do we know the entire ith column?
No, we
We don't, right?
lost the W thing in there.
We only know certain elements. Okay, so in particular, so in particular, if the we have what, M users and N movies. So if this particular user has only rated a few movies, right?
Right.
Then we don't know that entire column. So this is actually kind of incorrect. Okay. So what we do need to know is we need to concentrate only on these values. These are the Y values that I know. Okay. So what we will say is that we'll look at the index set. And I'll call it II. Well, not the best notation, but so I, subscript I, represents indices of movies rated by user I. Okay. And so now let's look at what the correct objective is, right? So let me denote by Ri, subscript Ri, as these values. So these values over here. This. So suppose II is just these three pairs, then this would be a vector of length 3. Okay. And remember that this is now going to pick out exactly exactly the corresponding rows of some particular subset of the matrix M. So it won't be the entire matrix M, right? It'll be a subset of the matrix M. Okay, so let me call that as M of II. Okay, so there'll only be 3 rows of the corresponding matrix. Okay, so for example, if I have these 3s, this will be 1, this will be 2, and this will be 3. Okay, so if I put these over here and assemble them into this matrix, this will be M, right? Okay, so similarly, if I assemble it over here, okay, then this is I, and this will be, okay, will be 3 rows if II is of size 3. And so I have MI times UI. Okay, and I still have that regularization. Okay. And, I can just put a half over here. And that is my objective. Okay. And let me call this objective as Ji. And I basically need to minimize this over UI. Any questions?
Excuse me, how do we decide the dimensionality of the latent space, like the K here?
So that's something that, we can actually just experiment with, but you can start off with 1K and you can just try different Ks and see. Typically, in machine learning, what will happen is that you will be given like a training set, and then there is a held out test set. Okay, so you can basically try different values of R and see how they perform on the test set. And typically, you also divide it into training set, validation set, and test set.
Right.
And you basically then try to find out the K or the rank that gives you the best performance. So clearly, too low a rank would be not good enough. It won't fit the data. It's kind of like that, the curve that we showed, right? That if you have too low, then you'll be underfitting. You have too high, you'll be overfitting, and there'll be some sweet spot. Okay, and you would do the same for other hyperparameters such as lambda also.
Right.
Okay.
Thanks.
Was there another question? Okay. And then, so this is my objective. And now I can, this is basically a ridge regression problem. Okay. And this is like a ridge regression problem where N, capital N, that we talked about in regression is actually just 3. Okay. So it'll actually give you some really interesting cases where, when we talked about regression, there was a dimensionality and there was the number of observations, D and N, right? Typically in regression problems, we assume that the number of measurements, which is N, is, greater than D or much greater than D. And here you'll see that there will be some times when, especially in the Netflix data, that, some users only rated a couple of movies. Some movies were only rated by a couple of users. So you actually get the other case also where the number of measurements is much smaller than the dimensionality, right? The dimensionality is fixed at K. Okay, so you will actually run across these issues when you kind of try to solve the problem, right? And so, I'm actually just rederiving it, right? But you can, solve this problem as a regression problem where you take the partial derivative with respect to UI, right? And what you will get is, this Ri minus Mi UI, right? You'll basically just get the residual, which is Ri II minus Mi UI, right? The half will cancel with the 2, right? And then you'll get a minus MII. Okay, this is basically just the analogous to the normal equations. Okay, so when I set this to be equal to 0, that implies that you have M of I transpose M of I. Okay, this should have been a transpose, I guess. Okay, plus lambda I UI is equal to MI transpose times RI. Okay, and one thing to note is that this will be a K by K matrix, nothing to do with M or N. Okay, this will be K times II matrix. And this will be our size. Okay. And suppose now I have that the size of II is equal to Ni. Okay. So what is the amount of computation which was involved? Okay. So let me actually try to do this quickly. MII is II by K, which is Ni by K. So I have to first form this matrix. Okay, and I'm actually doing this because you'll actually have this problem, right? You'll actually, for your homework, you'll actually need to do these computations. So forming this matrix will require, so it's, basically multiplication of two rectangular matrices. Okay, and this will be K squared times Ni operations. Solving the linear system. It's a K by K linear system. K by K linear system. Okay. You won't, you'll probably use some routine, right? But it'll take order cube, K cube operations. Okay, and so the total complexity of finding U from MI, is going to be equal to order K square summation of Ni over I. Okay. And that is equal to kind of number of ratings. So summation of Ni is basically the total number of ratings in the matrix times x square, K square. Maybe I should not. Times K square. Plus I have this part, right? Mk cube, and that needs to be solved mk times. K cube times. Okay. So this is the method of alternating least squares, alternating minimization. But the minimization problem is least squares at every step. Okay. And in some sense, it is a little expensive. Okay, because you have computation being cubic in K. Okay. And you can have other alternatives to solve this. And we'll see some of these methods later. Okay, so one is going to be a method that we will actually talk about quite a bit later on, which is stochastic gradient descent. Okay, descent, STD. Then we can also use other methods like coordinate descent and so on. Okay. But you'll see that this problem actually exposes different aspects of ridge regression that we have talked about. Okay, and you will see that, for example, you will not be able to do it without ridge regularization. You just will get an error when you try to do it, right? Because the matrix might be too small, or a particular matrices that you get might not be invertible. So any questions?
So if we could use SVD, if we just like multiply the W by R and then factorize it?
Sorry, but you cannot use the SVD, right?
Yeah,
Because
I'm just saying. Let's suppose that we could use SVD, then it,
uh-huh.
it would be like factorizing the Hadamard matrix times the R.
Yeah, I mean, I guess what you're saying is that can I just take W dot R, which
Right.
means that on the position that you don't know any ratings, you replace them by zeros, right?
Yeah, something like that.
Yeah, people actually have done that, and actually that's a good point. People have actually used that to try to initialize this iteration.
To come up with the U1 or M1 or something, right?
Yeah, exactly, exactly. And the issue is that SVD is actually a pretty complicated computation, which is kind of expensive, right? And many times what ends up happening is that you want to do this over millions or even billions of users and millions or 100 million movies, and then it just becomes computationally intractable to do the SVD.
Yeah, makes sense.
Yeah. Okay, any other questions on this? Okay, so I'm actually going to stop a little bit early, and I've mentioned a couple of times that we will give you your first homework is being given out today, and it'll be due next Friday.